Okay. Hi, everybody. Hi. Hopefully you guys got some outside time this weekend. We should have class outside. So a couple of reminders. Assignment 3 is out. It's been a little bit of a shaky start, but I think we're slowly getting everything under control for you guys. I apologize about that. But it should be fun. I mean, Intel will come through to give you access to this cluster of 100 Xeon Phis to play around with for this assignment. So that is a total of 6,200 cores that you can use. Well, probably don't want to use that for one job, but anyway, so when they can get everybody registered, you should have access to that by late Wednesday or Thursday at the latest. The one thing that they did tell me is that there's 2 requests they make of you. So you're the only class in the country that's being allowed to use this cluster, but it's under 2 conditions. One is if you have any questions about IT support, please go through my TAs. As in, the one guy over there does not want to be answering questions from 200 of you. So if you have any problems, please funnel it to the TAs via Piazza. My TAs will ask the questions for you. And the last thing is that for security reasons, they're going to restrict entry SSH into the machines to CMU IP address ranges, which is fine. You can just VPN into CMU and back out if you live off campus. But if you don't have VPN set up, you might want to go download the Cisco VPN client so you can work at home. So those are the only 2 restrictions. They said, we'd love for you to do it. It might be a little flying by the seat of our pants because they've never had more than like 20 people use this thing. So we'll see how it goes. Okay, and then another reminder is that exam 1 is next Wednesday. So a week from this Wednesday is exam 1. We'll put out details about timing. I tend to prefer having an evening exam to take time pressure off. And by evening exam, for those of you that have evening classes, we're very flexible in when you start that exam to avoid those classes if you prefer. So I will tell people out on Piazza, but is this something, a quick show of hands, is this something that you prefer or would not prefer? So how many people would prefer an evening exam that will be the same length as an in-class exam, but untimed? And how many people would prefer an in-class exam right here in this room for an hour and a half, same amount of, seems a little ambiguous. And for those of you that prefer the in-class exam, is that because you just want to get it over with? Or is that because you have a conflict with other things? You have conflicts with other things. So typically what we've done to avoid the conflicts is that we start the evening exam at 6 o'clock, and if anybody has a conflict, you can just get started at 4 or something like that. Would that change your mind? No? Okay. Well, I'll sort it out. We'll definitely try and make sure about 95% of the class is happy. Yes? Well, I mean, if it's in class, it is an hour and a half exam. And if it's out of class, it's an untimed exam. Now, people, I will take that up with you guys on Piazza because it wasn't abundantly clear. So let's get started today. And everybody ready? So last time I ended the lecture with this piece of code, because I want to review this a little bit. So I put this piece of code up on the board, and this is some code that's very likely that everybody might write at some point. Is both these programs, the left one and the right one, do the same thing. They just create a bunch of threads, and every thread is supposed to increment a counter. For example, that per thread counter might be a stats counter in your program, like how many times did this thread call this function? Or maybe it's a local reduction variable, like if you were accumulating a local mydiff, that's what you're adding into. And so last time I ran this program for you, and I ran it on actually a bigger core, my laptop. I ran it on the GHC machines with more threads than this. But we all observed that this program here on the right was substantially faster than this program here on the left. So first of all, what's the only difference between these 2 programs? What's the only difference between these 2 programs? Yes. Specifically, where this program it has an array of counters for every thread, one element per thread. This one has an array of counters for every thread, but I've separated the counters by one cache line. Every counter is by design on its own cache line. Now, I admit that this is pretty ugly code, but it certainly shows off a detail of how machines run. And so who can remind the rest of us why this code on the right, or each one of these counters that is being written to, runs significantly faster? And maybe I'll start with this question. Is there any data sharing in this application? Or really, I should say, is there any inherent data sharing in this application? Does one thread ever need to communicate data to another thread? No, right? Because every thread is just updating its own local counter. I agree. So there's no communication, inherent communication. What's the difference between how these two programs behave, or how the computer behaves, really? The cache coherent Intel CPU that I ran on, what are differences in how it behaves between these two programs? Yes, and that. So every time that a thread writes in this piece of code, the claim is that there is communication. And that communication is the machine doing what? In order to write to one of these integers, counter sub 2, you're saying that and specifically in terms of last lecture, the machine has to ensure that this particular core that's running this thread has exclusive access to the line. Because if it did not, what could happen? Here. Yeah, more or less. So I'm going to have multiple copies of this cache line in my system. I have a bunch of cores. They all have their own caches. Every one of those cores is going to bring this piece of data into their cache. And if all of them just start writing, different elements of that cache line will take on different values. And if that cache line is ever flushed out to memory, what's going to happen? Essentially, memory is going to have like zeros for all the other threads, and that could be really bad, right? So the main idea of last class was that if we want to have memory behave in a coherent manner, and we used a precise definition of coherence last time, but you can think about coherence as just a memory system that behaves much like you'd expect in a single-threaded memory, in a single-core memory system. If one processor writes a value, the other processor, if it reads it later, it should read that value. But we have this challenge because under the hood, that memory is implemented with a bunch of caches. And so the system has to exchange information to make sure that the data in all of those caches is coherent, or the same, essentially the same. So last class, we talked about some schemes for ensuring that memory was coherent. And if you had to summarize last class in like one or two sentences, what would you say is the main idea of how memory is kept coherent? So we talked a little bit about having to invalidate the line, or that's right. So the main idea is the way last class in these snooping-based schemes kept memory coherent is that every time a cache did something that would change its state, or at least the state bits in a cache line, it would need to yell out. It would say, "I'm doing this," to everybody in the room. And everybody in the room would listen to what I'm shouting out and then take the appropriate action. So if I said, "I'm writing to this," if all of us are behaving, we're not assuming a malicious computer here, if we're all behaving, if I said, "I'm going to write to slide 10," and all of you are helping me make the lecture, all of you immediately stop working on slide 10. Right? And sometimes if you are say, "Hey, I'm going to read slide 10," and if I was working on slide 10, I have to hear that and go, "Oh, you're about to read this, and I have a dirty copy, so let me give you the most up-to-date copy." So the name of the game is whenever you do something that changes the state of a cache line in your cache, you have to let all the other caches know, and vice versa. And the way we did that was we did that by broadcasting. Essentially, we did that by shouting. Whenever anything happened here, I'm going to tell all of you about it. Right? So if I said, if I have to write to address X and that address is not in my cache line, I'm going to say, I am writing to address X. And when I'm shouting out loud, nobody else is probably shouting out loud either because, well, that wouldn't make a lot of sense. So can anybody think of a problem with this approach of just shouting out loud every single time you want to make any change? That might work really well if like two of us are in the same room. But what about if like we were all processors, we were all caches? It sounds like we're going to have a scalability problem, right? Like if everybody is waiting to hear what everybody else has to say, that's going to be pretty challenging to implement, or at least it won't be very performant to implement. So today we're going to talk about how to do that more efficiently on much bigger systems. Before we go, I wanted to put up this graph from last time. So this graph is a plot of the cache misses taken by various applications. Just this is your Barnes Hut particles. This is your Ocean solver. This is a radix sort. Radiosity is like a grid-based solver. And the x-axis is the number of processors in the system, or the number of caches. And the y-axis is plotting the cache misses, but it's also attributing the cache misses to various aspects of caches, whether they be the 3 Cs that you heard about in 213 or 513, or some of the false sharing and true sharing misses that we've talked about in this class. So true sharing would mean what? Would that be inherent or artifactual communication? That would be inherent communication. I wrote a value, and you need to read it later, so we actually you have to take the cache miss to get the value. False sharing is very much the example that we just talked about. So what's the trend that you see in this graph? Certain types of misses. Oh, sorry, did I say the x-axis is the number of processors? Excuse me. The x-axis is the cache line size. So it's a much larger cache line going to the right. So what is the trend that you notice? First of all, something's going down, or many things are going down as the cache line gets bigger. And then many other things are going up. So a lot of the various types of missing sort of go down. Like the cold misses go down because you get more data for every cache line you load. The conflict misses, kind of depending on the app, might actually go up, depending on the associativity of the cache. The true sharing misses go down most of the time. Why would true sharing misses go down with a larger cache line? Because the same reason as the number of cold misses would go down. If those cache lines are big, presumably fewer cache lines need to be communicated. So this is not the amount of data. This is the number of cache misses. Okay, that's true. What else do we see here? This is an upgrade system, so I don't want to talk about upgrade traffic too much. But what about false sharing? False sharing is really going up on all of the workloads, but really most dramatically in radix sort, and also here in radiosity. So here's an interesting question. If false sharing does not go up with cache size, what does that tell you about the program? Let me think about that. That could be right, but let me see here. So you're saying that there's a lot of true sharing in the program, but there's not that much true sharing here like in Ocean Sim, and it's not that impacted by false. You don't see much false sharing at all because kind of if you think about the layout, if you just partition your data properly, you can avoid a situation like this. Or conversely, I can ask the question like, false sharing going way up as cache line size increases suggests what? So if you don't have a lot of spatial locality, and your accesses are kind of mixing all over the place, you're more likely that with these big cache lines, that 2 of your counters are going to fall on the same cache line, right? So it means that I have very fine-grained accesses to data, not a lot of spatial locality. Because if I had spatial locality, if I need something from a cache line, I probably need the rest of it as well. So spatial locality and cache line size kind of go hand in hand. And thinking about radix sort is actually an interesting example. Now, radix sort is not necessarily the best way to sort numbers on a parallel machine, but for the reasons I'm about to discuss. But if you remember, everybody remember radix sort is you end up sorting your array by the first R bits, of the numbers, and then you end up sorting by the next r bits of the numbers, and so on and so on. So a parallel radix sort, we might divide the array that you're trying to support up amongst my processor. I'm just going to partition the array equally amongst all these processors. And then I'm going to sort the elements that each processor has by their first r bits. So I'm going to locally sort the numbers based on the r bits. And then actually your implementation actually turns into a bit of a data parallel problem, meaning that the first part of P0 needs to go here. Then the first part of P1 needs to go right after the first part of P0, and so on and so on. And then like the next part of P0 goes after the first part of all of the processor stuff. So it's actually very much like this list compaction that you know pretty well at this point. So every number, every P0 might compute how many elements fall into each of the bins. You do a scan to compute where the starting offsets are for each P0. And then you actually just put the stuff in the bins. Like, for example, P2's elements, if these are the bins that they go into, might start here, 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 and here. So as you can see, if you don't have a lot of elements per processor, there's going to be a lot of false sharing, right? Because P1 is going to send elements right into this as well. But as you increase the number of elements per processor, my claim is that false sharing might go down. And can anybody see why false sharing would go down as the data set size increases? Yeah. Okay, and so to be very specific, false sharing here might be P2 is trying to write these values. P1 might be trying to write values into the blue bin right next to it. And even though there's no communication, these might all land on the same cache line, and that cache line is going to be bouncing back and forth between P1 and P2. So as the number of elements in the array, clearly as the cache line size increases, it's just going to be more and more likely that multiple processors are writing the same line. That one makes a lot of sense. But can you see why if I keep the cache line constant, if I make a much bigger array, false sharing might just disappear? Yeah. It's much lower because P2 is going to have a lot more blue elements to write into the consecutive element of the array, right? And so that means there's going to be much greater spatial locality in those writes. And so many cache lines might entirely be written over by one processor, and there'll be less false sharing. Yes? Well, you don't know because you don't know how many numbers fall in each bin. But yes, that would have been a good tactic had I known. True. Okay, so let's think about one more detail from last lecture. Is everything I've said so far is a processor has a cache. And all of those caches need to communicate. But every processor you've probably seen or worked on has an L1, an L2, an L3. So there might be a question of, well, what's going on here? Because we've kind of thought about this whole thing as there's cores and there's like an L1. But now there's like an L2 behind that L1 and a shared L3. So in a real system, we have to take some care to make sure that data is not just copied once per processor, but 2 or maybe even 3 times per processor. So it can get even more complex. So has anybody heard of if I said the inclusion property of caches, does that make any sense? Is that a term that you have heard? Probably not. It is a term you've heard? What is the inclusion property of caches? Correct. So a cache hierarchy, very good. So the cache hierarchy enforces an inclusion property if everything that's in the L2, everything that's in the L1 is also in the L2. So an interesting question is that automatically maintained if L2 is bigger than L1? You just get inclusion for free. If I said I want a system that has inclusion, would you just look at it and go, well, yeah, the L2 is much bigger than L1, so clearly everything that's in the L2 will probably also be in the L1. Any thoughts? You had that? I see. Yeah, I would ignore that case. But so let me just give you a quick example. The answer is absolutely not. But let me give you a quick example with two simple two-way set associative caches. So in general, this is certainly not true. So imagine that you read the value A, right? So you read the value A, kind of like what you said, like L2 loads the value, brings it into L1, and we're all happy. And let's say that we also read the value B, and the address A and B happen to map to the same set in these caches. Okay? So if this is an LRU, the most recently used data is B, and the most recently used data is B in both caches. Right? So now imagine that the processor just kind of goes to town and does a lot of work on A. Accesses A over and over and over again. So these are all cache hits. So now the most recently used value is A in the L1 and B in the L2. Right? Because L2 never saw any of those cache accesses. So if we come in with a new request, like a request C, that also maps to that same set, L1 and L2 both need to perform some eviction, and if they just go with their least recently used policy, they're going to evict different values. So inclusion is not just maintained by default by the nature of a bigger cache being the L2. But there's a lot of tricks you can do to maintain inclusion. Like, for example, if a line is evicted in the L2 cache, oh, sorry. So let's just think about how this works. So imagine that we have an L1 and L2. And remember last time I said that the cache for every processor is listening for all of these shouting requests. Well, the cache that's listening is the L2 cache. Because the L2 cache is what's stuck right on the interconnect and can see everything that you hear, or can hear all the shouting. So if the L2 observes, oh, wait a minute, I need to drop my line because somebody else is writing. Well, before the L2 kind of nods its head and goes, okay, sure, I'll drop my line, it actually needs to tell the L1, hey, look, you need to drop this as well. Because someone else in the system is trying to write to it. I'm dropping my line so that I don't have a stale copy. Hey, L1 or higher up the chain, you need to drop that as well. Because otherwise, we would have violated coherence already. So bus read X comes in from externally. Cache goes, ooh, wait a minute, I have the value. Well, inclusion is held. So everything in the, there's a bit on the cache line that says, hey, look, you know, the L2 can just immediately tell if it's in the L1. If the line is in the L1, we're going to go ahead and tell the L1 to invalidate. And that is the point at which the original L2 cache can respond to the original shouter, say, okay, we're cool. You can go ahead. There's some other details, like, for example, assume that the L1 is a write back, like you'd expect, and line X in L2 is dirty. Is dirty, is not dirty, but has an exclusive access because the processor has written to the value at some point in the past. So at this point, the most up-to-date value is in the L1 cache. We're guaranteed that no other processors in the system have the value because that's the definition of coherence. But the L2 hears somebody say, I need the value X. So the L2 has to say, whoa, 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 the L1 has the most up-to-date value. I need to ask the L1 to flush, grab the latest copy of the data, flush it out to memory, and then we'll all either go to the shared state or drop the line. So there's a lot of complexity in these multi-level cache hierarchies to maintain coherence. And typically, you should think about it as whatever cache is connected to the rest of the system is the cache that's executing the coherence protocol. And it's responsible for the rest of the memory hierarchy up the chain to follow suit for whatever they want to do. So point being, there's a lot of messages being sent around in a modern processor to actually keep memory coherent, even when there's no actual sharing. Because even if there's no actual sharing, we still have to tell everybody else what we're doing, just in case there was sharing. That's one of the reasons why if you go look at an NVIDIA GPU, you will not see an implementation of coherence at all. So all of these different cores, if you make a write on one NVIDIA core, and a processor in another SM makes a read, there is absolutely no guarantee you will ever get the value of that write without special things being taken by the system. And there's some ways that, for example, the world makes it seem much more coherent. Like, for example, after every CUDA kernel call, like when you call to kernels, you better believe that there's some form of a flush of the caches out to memory so that all that data, when you read it in the next kernel call, actually appears to you like it was written out to memory. Other things that happen to make things a little bit more sane is the L1 by default is actually right through in an NVIDIA processor. So it at least goes all the way out to the, the L1 goes all the way out to the L2. And if you do a global memory atomic, the global memory atomic is actually implemented in the L2 because that's the single shared cache. So all the different cores, when you do global memory atomic, it's actually carried out by logic in the L2 because you don't have to worry about coherence at that point. There's only one of them. And if you look at the assembly for NVIDIA, you can see some interesting things. There's a lot of modifiers on loads and stores. It's like load but skip the L1, store but write through the L1 and skip the L2. Like there's a whole bunch of little things you can do in software as needed, but the hardware is not sending all these messages around by default. So there's some arguments about whether or not GPUs should have coherence, and thus far NVIDIA has said we are not going to pay the price that it takes to implement this thing because, as you saw in assignment 2, that wasn't a coherent memory system, and did okay. Did okay. Okay, so any questions about like the gist of cache coherence before we start talking about better implementations? Yeah. It's an interesting question that a lot of people are asking right now. So first of all, you certainly want, if you're an operating system developer, you want memory to behave very much like a shared address. Like, so here's another example: is if one thread in a CPU in a normal program writes values out to memory. Let's say you do the appropriate synchronization just to make sure that there's no race conditions or something like that, and another thread goes to read that memory. You expect the values to be up to date, right? So imagine that you're on a non-coherent system. Let's just actually take a GPU-CPU case. Imagine that you're on the CPU and you write some bytes into memory, like on a SoC, like an Apple phone or a Qualcomm phone, where both the GPU and the CPU share the same physical, right? You write it to memory, you hand the pointer off to the GPU, and you say run. You read the data, and it's stale. It's not there. So without coherence, you have to inject, the operating system has to inject the appropriate flushes and things like that into the handoff. And if you're running through a driver, like you do with CUDA, well, the driver is doing that for you, potentially at some cost. If you want to start treating a modern system as a heterogeneous bag of cores, some GPU cores, some CPU cores, which is where the world is going, as a developer, you don't want to be thinking about when do I have to be flushing my caches, when do I not have to be flushing my caches. So if you look at an Intel GPU today on a modern Skylake chip, the CPU and the GPU are coherent. So you can write to a pointer on the CPU, you can pass that pointer to the GPU, the GPU pointer can just dereference the pointer, and the data's there. The L2s will flush and everything like that as you'd expect. So if you want to have a system, and you don't want to be thinking about what data is stale, what data is not stale, coherence is really, really useful. If you're implementing locks or synchronization, you do an operating system-like things, coherence is also really, really useful. If you're just implementing it at the application level, as you kind of see from CUDA, not as much. Not as much. The code that you would write that's doing fine-grained bouncing of data around the chip is probably so not performant anyway because of communication. You want to restructure your code to avoid that. Okay, so yeah. Okay, so the name of the game is, any other questions? Whenever a cache miss occurs, everybody has to hear about it. That's the name of the game at this point in the lecture. Okay. Now, I want to scale up now to bigger machines. So we can think about this as machines that, like a big rack in a supercomputer where I have a whole bunch of blades of processors, each with their own memory. We can think about this in a modern sense as I want to have a 64-core processor, such as the ones that you'll work on in assignment 3. So I have almost a little supercomputer on a chip, and I don't want every single one of those cores to have to talk to every single other one of those cores every single time it takes a cache miss. So I just want you to think about a bigger system where up until now, whenever any processor wants to do something, it has to tell everybody else. And so you should be pretty scared about this. And sometimes, telling your next door neighbor might be a lot cheaper than telling somebody on the other side of the chip. So if you hear this term CC-NUMA, that is a shared address space that provides non-uniform memory access and is cache coherent. This is a big term from the 90s and early 2000s. These days, I think it's more of like what every system does. So it's not nearly as big. So what are some ways we could do better? So right now, if I have to make a change to the state of my cache, I have to tell all of you. If you're a computer scientist, you have a lot of ways to avoid broadcast in your toolbox. So what are some of those ways? If something doesn't scale, what's the first thing you do in computer science? You build a hierarchy. You almost always build a hierarchy in computer science. So if we had one interconnect that was handling all this traffic, we could partition the machine in two and say, okay, we're going to shout to all our neighbors on this side of the room, and all the people on this side of the room will shout amongst themselves. And if you ever have to talk to the other side of the room, we'll funnel it through a set of people that are responsible for that. Right? And we could scale this up. We could definitely continue to scale this up, right? Like we could have different topologies. Maybe there's a different memory for each side of the machine to keep it local. But, and we could do everything we talked about last year sort of in this hierarchical fashion. But, that doesn't work that great. It doesn't work because, you have this bottleneck at the root. If you have an application that's communicating from one side of the room to the other. There's now more latencies because there's extra steps in this process. And remember, this is happening on cache misses, so it needs to be fast. And this tree structure doesn't really make a lot of sense if you have a complicated network that doesn't look at all like a tree. Like if your network is a grid or a torus or something like that. So today what I want to talk about is I want to talk about an alternative way to implement coherence that does not involve telling everybody what you're doing. So this is a very, this is the more shy version of coherence. Okay, and the main idea is that instead of everybody working this out in a distributed fashion, there's going to be one place in the machine that maintains the information about a cache line chunk of memory. So before, I'm going to check with all of you to see what the state of your cache is. Now if I want to know who has this piece of information, I'm going to go look it up in a book. And that book is called the directory. So for every if we have a 64-byte cache line, for every 64-byte cache line in the machine, there's going to be a place where I can go look and I can ask the question, hey, what caches are currently holding this data? Okay. So we can think about it like this. So if I have a processor and there's some memory, and let's say I'm going to chunk this memory up into cache line size chunks. So if this was an Intel processor, that would be how big? 64 bytes, right? So now what I'm going to do is I'm going to augment that memory with a directory. So for every line of memory, I'm going to store some extra information. So maybe it might be easier for you to think about that extra information being out over here. But that extra information is sort of the state of the line in the various processors' caches. So for example, if I have a P processor system, I can have a little bit vector here, which has a bit in position I if this line is currently cached by processor I. So the answer is right there. So the directory stores this processor, these processors have the data, and maybe an extra bit which says, hey, one of them actually has a dirty copy of it, so memory is not up to date. So let's think about a system. Here's an unusual system with 3 processors, because that's what I decided to draw when I ran out of room. And every processor, and memory in this particular case is distributed across the processors. Now you can think of memory being all in one place as well, and that's equally valid. But what's important is that every line in memory has a directory, has a home node in this case, or a directory entry that basically is the roadmap for what it's doing. So in this case, I'm going to call the home node of a line is the node that owns that memory. And really the node that owns the directory entry for that memory. And if I'm a processor and I'm issuing a load or a store instruction, the processor that wants the data is the requesting node. So I have a requesting node, and the requesting node is going to have to phone home to figure out whether or not, or what it should do next to get the data. So back last lecture, if a processor wanted to access data, what did it do first? So it shouted, but what did it actually shout out? What information did it say? In a snooping protocol like last time, processor wants to load data, what did it do first? Yes. It said, this I am going to read or write to this address. I'm letting everybody know. And why was last time called a snooping protocol? Where did that term come from? Well, it's kind of the opposite. Everybody else is kind of listening in on everybody else's business. Right? So every one of you are listening to say, if this cache is doing that, I need to do this. And there's a protocol that's carried out to ensure coherence. Now, what's going to happen is, if this processor has to make a memory operation, it's not going to yell out, this is what I'm going to do. It's going to go to the directory, or it's going to go to the home node of that address, and tell only the home node, hey, I need to do a write to this address. Tell me what I need to do. So does the difference make sense? OK. So that's exactly what's going to happen. It's the processor 0 is going to send a message over to the directory and say, hey, I'd really like to read this value. And the directory, in this case, is going to say, hey, look, OK, go for it, because nobody else has this data cached. So I'm illustrating this by saying that the directory entry, all the bits, the 3 bits in the bit vector, they're all 0. So nobody else has it. And so the processor 1 can just load that line in what state? Shared, or shared clean. Sorry, shared exclusive if it was messy. If it was MSI, it would just be the shared state, because it's a read request, right? Yeah. OK. And now notice that I turned on a line in the directory to indicate that this address, cache 0, now has it. Make sense? OK. So now what would have happened if, when processor 0 went and asked the directory in node 1, hey, I'd like to read address X, what do you think would have happened if the directory said, oh, processor 2 has the data? Just in a read state, in an unmodified state. Processor 2 had the data. So in this case, there would have been a red dot over here for processor 2, and the dirty bit would have stayed off. Yeah, so basically what would have happened is all the red lines would have stayed the same, and the result would be bits 0 and 2 are on, right? Okay. But now what would happen if it looked like this? So now we're saying that processor 2 has the line that I want in its cache, which is indicated by the blue line being over there in the cache. And the directory says, oh, and processor 2 had the intent to write, so I'm going to consider it dirty. So what do you think happens now? So processor 2 at this point has no knowledge that I intend to read that value, because I'm not shouting out loud anymore. I'm just kind of saying, hey, directory, I kind of want address X. What do you think is going to happen next? Yeah. So someone has to tell processor 2. And in this particular scenario, let's say that the directory responds to the requester saying, hey, what you need to know is that processor 2 has it and it's dirty. So that's what this response might be. It might say, oh, well, you want to write it? Well, go get it from processor 2. Good. So it says, hey, I don't have the data. Processor 2 has it. Go ask them. OK, so what do you think happens next? So now I need to say, oh, somebody just gave me directions. So now I'm going to go walk over to processor 2 and say, hey, man, I kind of need this data. And it sounds like somebody told me you had it dirty. And so processor 2 is going to say, OK, I will do what? I will drop the line and flush. And then, or there's some options, actually. So in this case, I'm going to go to processor 2. I'm going to say, hey, hey, I want that data. And processor 2 could flush it out to memory, or really, even if it flushes it out to memory, from memory it then needs to get sent back to me, right? And then last, there's also processor 2 needs to go back and tell the directory, or someone needs to tell the directory, hey, look, it's now not dirty. and that here are the two sharers. So why are there still 2 red dots given the MSI protocol from last year, or last week? Why 2 dots? Processor 2 decided to keep it cached, which is fine. It flushed the value out to memory and kept it in cache. Processor 0 also has it in cache, and both of them can read just fine. Exactly. So what's the big difference between this approach and the previous approach? What happened to all the shouting? What happened to all the broadcasts? We've turned broadcasts. Exactly. So we've changed yelling or broadcasting messages into a sequence of point-to-point messages between the relevant parties. And we have a traffic cop. We have a director, which is the directory, to kind of sort this out, or a concierge if you want to use your example. Okay. So what happens if processor 0 wants to write to this particular cache line, and processor 1 and 2 already have it in their cache? Exactly. So the directory is going to tell me, hey, you need to tell processor 1 and 2 what that you're going to write, because that's who has it. I will notify them. They will drop their line, and as soon as I get confirmation that they've dropped the line, I can now proceed. And notice that the directory has been updated as appropriate. Yeah. Well, in this case, all of these examples are assuming that the address X that I'm referring to, its home node is processor 1. If I wanted to access address Y, and address Y's home node happened to be processor 2, then all my arrows would have gone over there. So this is just an example. Okay. And then the last is that processor 0 obviously needs to wait to make sure that processors 1 and 2 have dropped the line. So we have this 4, there's actually 5 messages, but some of these messages can actually occur in parallel. You can, and in this particular example, I'm just saying, let's imagine a machine where the memory is distributed by the processors. Okay? So I could have drawn the exact same diagram with one single memory down here, with one single directory right next to it. But I do want to differentiate between the home nodes, because that's more representative of a very big system. And in fact, it's actually representative of Xeon Phi, and I'll show you that at the end of the lecture. Okay. So what would you say is the advantage of a directory compared to the snooping protocols from last time? So we're carrying out the exact same protocol. It's still MSI or Messi or whatever, but we're doing it with point-to-point messages rather than broadcast. Why is this potentially a good idea, and why might it be a very bad idea? So imagine if all of us were caches, and only like 3 of us had a cache line, and I want to write to it. It's much better for me to just walk over to you and say, hey, could you drop the line, please, rather than bothering everybody in the room, right? Where's a situation where this might not be such a good idea? Like, imagine I want to announce the review session for the exam, and I have to compose an email to every single one of you. That would be very frustrating and probably wouldn't be very efficient. Right? So if you need to communicate with everybody, broadcast can be very, very efficient. So this directory is sorting things out for me, is that it's assuming that a small percentage of the processes are going to have the line. And in that case, it makes more sense for me to communicate with the directory and me to communicate individually with each one of you about what to do next. Okay. So like if all the caches were sharing data like you pointed out, like I'd be like, gosh. So what do you think is actually true? Do you think in general most processors are sharing data, or most processors are not? And by sharing, I don't actually mean communicating. They could all have the value in their cache in a read-only state. It's an interesting question. So as you can imagine, some folks have done some studies. So here are 3 graphs, and this is a histogram of, given the number of reads or writes, I think it's any memory access, so 3 different applications. This is actually for when writes occur, excuse me, is the number of caches that have the data in cache in a 64 processor system. So does the graph make sense? So if all the data was always in all the caches, you would have zeros, and then all the data would be here. So first of all, what do you notice about these trends? Does it make sense to use a broadcast mechanism to implement coherence? Or does a directory maybe have some merit?
Well, it looks like basically no more than 5 or 4 clusters ever had distribution. So it feels like it's unnecessary. It's never going to resolve that.
Well, never is a strong word.
Okay, well.
Never is a strong word, right? So all of the applications have situations where a processor goes to write, and all of the other caches have the data. So what would you actually say? Most of the time. So the common case is that very few processors have the data. But we need a solution that works out there, otherwise we don't have a coherent system. So, and if you think about through all the access patterns, it actually turns out that most of the time, these graphs hold. And then, like, if you kind of think through it, you're like, oh yeah, that kind of makes sense, right? So, for example, imagine a piece of data that everybody almost always reads. Well, if everybody always reads, is that going to be a data? What is that going to look like on one of these graphs? Let's just say that a value is read all the time and rarely written to. What will the histogram look like? It's going to be way down here. Like, there's going to be a huge bar over here, right? So wait a minute, isn't that a bad idea? So why is a directory okay in this situation? Because the writes are what we care about, and the writes are infrequent by definition. Good. Here's another example. Maybe like we have a token and we're passing it around. Like, I'm going to give it to you, and then you're going to give it to the next processor, and so on and so on and so on. What is that access pattern going to look like? How many shares are there going to be? Let's say I write to it, I hand it off to you, you write to it, you hand it off to your friend, so on and so on and so on. Are there a lot of shares? Yes or no? Some people are nodding yes, and other people are nodding no. So actually, there's a little bit of disagreement here. Yes? That's right, and if it's really a handoff scenario, you're going to read it after I wrote it, but if I just wrote it, I invalidated everybody else's cache, so when you go to read it or write to it again, you're only invalidating me. So in a token passing scenario, there's not a lot of shares. If we have frequently written objects, you might be like, oh, that's a problem, if it's like a really frequently read object. But it turns out if they were always writing objects, we're always invalidating all the readers, which means that there's not a lot of time for a bunch of readers to build up. So a bunch of writes is actually a situation where it stays low as well. So in general, when you think through a bunch of cases, you're like, wow, in most of the cases, the number of shares is going to be low. So this gives us 2 options. First of all, or two insights. It says, first of all, this idea of me only talking to a few of you, well, this makes a lot of sense, because I don't want to bother you on this side of the room if I'm going to tell these guys something. Moreover, it actually seems like there are ways to not necessarily store a bit per processor. Because like if I have a big machine, a bit per processor can get kind of crazy, right? So imagine that we have this system like I talked about, and imagine that a cache line size is 64 bytes, and P is 256 processors, which is big for a single core, but not insane. So what is the size of the directory in this case? How many bits do I need? Or how many bytes do I need? How many bytes do I need to store the directory? Think about it as per cache line. Okay, let me make it easier. How many bits do I need? 256. I mean, let's ignore the 1. Yeah. So I have 32 bytes that I need to store the directory for every 64 bytes of real data. So if I have like 16 gig of memory, I have an 8 gigabyte directory. That seems maybe not so tenable, right? Okay. So the way we've been talking about it so far is we have p bits per cache line size chunk of memory. And if I divide all my memory up by 64 bytes, that tells me how many different directory entries I have. And, you know, I want to scale to a 1,000 node core processor. All of a sudden, my directory is twice as big as main memory, which seems like a high cost to pay for coherence, right? So how can we do better? So right now, I'm going to store a bit vector that encodes, you know, who's got this. And let's say I want to scale up to these big machines. How can I do better? Yeah. OK, how are you going to do that? OK. OK, so let's just take this case, 1,024 nodes, because it's easy math. How many bits do I need to encode an ID? Which is 10. Right, so I need 10 bits per ID. OK, so the math is easy. But I have 1,024 processors, so in the scenario where you all want the data, I need 1,024 by 10. So that's So we need a solution that works. I like where you're going with this. But let's just keep going. So now I need a way to encode this list. And most of the time, let's say if there's only like 3 shares, your idea is great because you only need 30 bits. And your 30 bits is way better than the 1,024 bits here. OK, so if there's coherence and access, I can maybe encode the bounds. Yeah, OK, that's getting there. But what if there's not? What if I want every other processor? That, and this is not a little tricky problem, right? Or just, OK, what is it? Well, that sounded a lot like your idea in that we're just going to store 3 numbers. But a sparse matrix can also encode a dense matrix. And so what are you going to do in that situation is my question. Let me go back here, and then I'll come back. Yeah. Do you have something now? OK. So let's not think about it as like the actual latency, but you could actually think about it as number of hops. Right, so broadcast, you know, the nice thing about a broadcast network is that there's not a long chain of operations that needs to occur. You know, the span of the operation is essentially O of 1. The problem with broadcast is that we're all contending for that same resource. So the thing that's not so good here, or is potentially problematic here, is that now in order to perform my coherence transactions, I'm going to have to go to a directory and then go somewhere else. Whereas before, I used to shout, and presumably if I had a shared bus, it would get everywhere on the machine in roughly equal time, at the cost of contention for that shared resource. Is that? Well, it's certainly true that we could imagine a system like this one, where processor 0 accessing processor 1's cache in a snooping situation, or the directory on node 1 is quicker than getting all the way over to node 2. And that is very much the essence of NUMA, in that the address that you are accessing will dictate the latency of the operation. That's absolutely true. And that can cause problems if you're a hardware architect. Because notice how I said, I have to wait for you to acknowledge that you've dropped the line before I can proceed. It means that how long I have to wait now is variable and things like that. So it can get quite tricky. It can get quite tricky. Does that answer the question? Well, the directory, yeah, so given what we've stated so far, absolutely, yeah, the directory is out there in memory. Now, of course, you could cache the directory. You can always cache the contents of memory as well. And that is absolutely true. It does happen. So you could think about it as cache for now. But in the same way that address translation might incur a TLB miss and make it even harder to translate an address, a directory lookup can miss a directory cache and take even longer to carry out the coherence traffic. So if you have a dual socket Intel system these days, actually there is a little bit of directory work done to keep because both processors view the same memory, right? They actually have a directory on both sides of the QuickPath interconnect. And inside a QuickPath, there's a little cache of the directory that sits out in main memory. So everything you can do in memory, you can do with a directory as well. OK. So any other ideas? Yeah, you have. It makes sense. And if you're hashing, it's basically like you're saying you're going to have a content addressable lookup. You're going to have a cache. But the question is, what happens when you have to spill? Because I can't just like forget who's sharing the cache line. So I want you to think a little bit about how you often design systems. And I'll come back to this a little bit. But we want a system that, in general, is very compact. Because most of the time, there aren't very many shares. But we have to be able to represent this case of all the shares. So nobody said we're going to use your scheme, which sounds perfectly fine. And then if we run off, let's say I give you 30 bits up to 3 shares. If all of a sudden we get 4 shares, maybe we just invalidate all the caches. Very rarely happens. Or maybe I have a bit that says all the caches have it, or something like that, right? Or maybe I start using one of my bits to actually represent close to your idea of now 1 bit for every 3 processors, or something like that as well. OK, so let's talk through some of these things. So one of them is, well, we could actually just increase the cache line size. Which increases the sharing granularity. We can group multiple processors into a single bit. But let me give you two alternatives. So the first one is called a limited pointer scheme, which is exactly what you proposed. Rather than storing a bit vector, I'm going to store a list. And in the 1,000 processor case, I can get 100 pointers for the cost of the 1,024 bits, right? And like this suggests that would be great most of the time. And then we can just, whenever we detect that we run out of bits, we can do something else. Like as soon as we run off, we can just decide to flush all the caches and start over or something like that. Because presumably that doesn't happen very often. Or we can have a special case for the all sharing. So I'll just use 1 bit to say everybody has it or they don't. Or something like that. So you can kind of think of these things. What are some other, did I get all the... Yeah, the other option is you could just fall back to broadcast. You can fall back to a snooping-based implementation, which typically isn't possible because you don't have a broadcast network. But all of these, I think, are really good examples of a principle that you probably want to apply in any type of computing, right? Is you want to optimize for the common case. You want a solution that is elegant, simple, and works well most of the time. And a fallback that will handle all the other cases that may not work very quickly. And why is it OK for my fallback to be inefficient? Because it doesn't happen very often, right? So in general, if like 0.01% of the time I'm running off the shares list, it's sort of OK if we handle that with an abacus or something like that. OK. So all of these techniques were about compressing the width of this directory like this. But it didn't really combat the problem that there still needed to be a directory for all of these entries in memory. If we're talking about a modern machine with, Professor Blowick just bought a machine around here that has a terabyte of main memory. That could be a pretty big directory, right? So the question is, do we even really need to maintain directory information for most of these lines in memory? Because most of these lines in memory, the list looks like what? It's blank. And why is it blank? Most of the main memory is not in cache, right? And things are only non-zero in these lists when stuff's in cache. So, like the observation here is that most of memory is not cached. In fact, less than 1% most of the time. So a number of folks have tried to sort of exploit this at the cost of kind of an insane amount of complexity in these systems. So one example is, let me start with your idea, and let's just say that I have a cache, a small cache that's my directory. And maybe I'll size that cache to be like this huge fully associative cache, or close to fully associative, that's about the size of the aggregate cache in all the machine So it's not a directory that's the size of all of memory. It's a directory that's the size of cache. So if I have an address that's in one of the caches, I put it into that directory, that little directory. And then all that directory does, and again, like this is, I'm saying like these are kind of getting extreme. This is not stuff that modern systems will do. Is, well, that directory can just point to the first cache that actually has the line in it. And then that cache, if there's any other share, well, I can use some bits in the cache to maintain the idea of the next cache that actually has the line. And so on and so on. So the list is actually not implemented out in the directory, but the list of shares is implemented as metadata in the cache. So I've kind of built up this linked list. So if I want to add to the list of shares, how would I do that in this case? So if let's say a processor says, I want to read a value, and all these other processors have it, but it is not stale, the implementation would just be what? It would just be adding that processor, load it into your cache, and make your cache the head of the list, O of 1. Now what happens if I want to add, if I want to write to a value? I have to invalidate all the shares, and what would that entail? Now it entails actually walking down this list, and so I have an O of n or O of p latency of a write, which can be quite bad. What happens if I just invalidate an item, if I just flush an item from my cache? Like let's say node 0 says, you know what, flush. Now all of a sudden I'm in like a linked list removal scenario where I have to patch up the linked list. So you can imagine that even though there's been some research papers written about this stuff, this is a very software-y thinking of how to handle the list, and so it's not really implemented as much in practice. Okay, so just a few more notes. So I started this part of the lecture by putting up all of these arrows, right? So if there was a write miss, we would have to tell the directory. The directory would tell me who has the data. Then I'm going to go over to all the shares and say drop the line. And then I'm going to wait for all of these shares to get back to me. And then finally, when they get back to me, then I'll go ahead and start my write, and so on and so on. So your question about latency, unrelated to going out to memory, is just there's a lot of messages we have to exchange to implement this protocol. And so there are ways to sort of be a little bit smarter at the cost of some complexity to eliminate messages. Like, for example, if we're reading a value from a dirty line, and a lot of these things are actually pretty obvious from a software perspective, but pretty hard to implement correctly in hardware. So the directory could just say, so this was the read miss. So again, to review is, I ask the directory tells me who has it, I ask the data, I ask the node for the data, the node gets back to me and sends a message to update the directory. And we can kind of eliminate some of these things. Like, for example, I can ask the node for data. The data can directly ask the node that has it for the data. The data can come back, and then the directory can just respond to me. So I've eliminated a message but kept the critical path the same, right? So again, let me go back. I ask the directory phones the owning node, or the dirty node gets back to directory gets back to me. So I left out a message. Other ideas might be I ask the directory tells the dirty node just immediately gets back to me and sends me a message. And I go, oh, okay, thanks. So now you can see how these things are getting a little bit more complicated, because now, like, I asked the directory for a message and got a response back from somebody else with the answer, right? So you can imagine if you're trying to be lock-free and stuff like this, it can get a little bit complicated to be correct. So there's a lot of different ways to minimize the amount of messages. So going back to reality a little bit in 2017, here again is the cache hierarchy for probably almost any machine that you've worked on in the last 5 or 6 years. Is there's an L1 data, an L2 data, an interconnect, and then a shared L3. So does anybody kind of know how it works on an Intel processor, how coherence works? So what needs to be kept coherent? The major agents of coherence basically are these L2 caches, right? Because that's what's on the interconnect. But there's actually something really, really useful going on here, is that those L2s are backed by a shared L3. So remember that, like, is there a coherence problem with the L3? why is there no coherence problem in an L3? Because there's only one of them, right? So it's not like we would ever need to know. Oh, and the L3 is inclusive with the L2s, meaning that anything that's in an L2 is also in the L3, which is hopefully not that big of a deal because the L3 is so huge. So it's pretty interesting. So now, whenever an L2 takes a miss, well, one thing you could do is you could just shout out to all the other L2s. It's stupid. But actually what happens is the L2 goes and looks up the answer in the directory. Now, this directory is not stored out in main memory because we don't care about all the memory. We only care about addresses that may be in the other caches. So where can we go to figure out what addresses are in the other caches? Well, we can go exactly to the L3 because it's inclusive. So any line in the L3 has 4 bits right next to it, which is the brute force 4-bit directory for P processors. So if an L2 takes a miss, it asks the L3, who are the other sharers? The L3 uses its 4 bits on that cache line to tell you who the sharers are. And then that message, then I go over to the other core in the chip. And so even in a 4-core processor, you actually have a directory-based scheme these days to minimize the amount of shouting or traffic that's going on over the shared interconnect. And it's pretty interesting. So this inclusive property means that the directory has to be only as big as the L3. It doesn't have to be as big as main memory. So this can be very useful. When we have a 2-socket system, you kind of have the same thing, but it gets a little bit more complicated now. Is that some of the, so a 2-socket system these days typically has 2 different interfaces to memory for each of the sockets, or different channels to memory, usually with an affinity to each of the sockets. So this is why I was drawing that diagram at the beginning of class as memory being very close to the processor. So if you went out and just bought a simple 2-socket server these days, you're going to have a single machine that needs to be coherent. The directory in the L3 can handle coherence here. The directory in L3 can handle coherence here. But if these processors access data that is owned on this side of the quick path interconnect, there's going to have to be some exchange of information between the 2 directories in the L3s as well. Right. And to your question, that directory is stored out in memory in limited cases, but there is a cache of that directory in the in the home agent for every one of these cores to handle the multi-socket coherence case. The details of how that all works, I don't know, and I'm not sure if it's very public, but it would be interesting if anybody does know. And then these issues in 2017 are now very much cropping up, on a single chip. So here is Xeon Phi, which is Intel's sort of like high-performance supercomputing / machine learning-like chip that they're trying to build that looks a lot like a GPU in number of cores and stuff like that. So Xeon Phi is 72 x86 cores with AVX 512 instructions. So if AVX is 8 wide, AVX 512 is 512-bit instructions, so it's 16 wide scalar vector operations. So we have 72 cores. You can kind of just see it in the diagram. Each one of those cores is 4-way hyper-threaded now, not 2. Some of the instruction pipeline latencies are 4 instructions. So why does it make sense for a 4-wide, instruction latency 4 pipeline to have 4-way multi-threading? High latency, exactly. So if you have 0 ILP, you can probably still run very close to full rate. Right? So these things are grouped. The cores are grouped in pairs of 2 into like these 36 tiles. So 72 divided by 2 is 36. It's L2 cache per tile. So every core has an L1. Groups of 2 cores share an L2, which actually means that effectively from the coherence protocol, it's actually a 36-node chip, not a 72-core chip. And that you have a mesh interconnect that is connecting all the tiles. Right? And there can be there's 16 gigabytes of actual DRAM on the package itself. So you've got your chip, you've got DRAM, and you've got the packaging enclosing them both. And I'll have a lecture on that later. But so there's 16 gigabytes of almost on chip, on package DRAM that you have really high bandwidth to, and then of course traditional DDR off chip. So notice that these different memories are very much closer to different processors as well on the interconnect. And coherence, so the nodes are organized as a mesh, so now you're only seeing the tiles, not the cores, so you're seeing 36 tiles. And routing on this mesh is what's called XY routing. So if you want to get from point A to point B, you will go in your row, and then you will go in your column. That's how stuff is routed. And the directory is sort of spread out across various parts of the chip. Different tiles own different parts of the directory. And you can actually set up this directory at boot time. It's kind of like I think it's an operating system boot parameter, where you can put the directory in a couple of different modes. Like, for example, you can say that I want to hash these addresses using this hash to these tiles. Or you don't say that. You say, I want a hash. So essentially, the home node for an address is selected at random on the chip. And so the coherence traffic would be, let's say that that tile up there is requesting an address, and that address happens to hash to this directory. The system will send the message, again with XY routing, to this node. And let's say the directory is doesn't have the data, or says it's not in cache. Then it will bounce the node out to memory, and then memory will respond back to the requesting core. So it's kind of the example of the request forwarding example from earlier in the class. A slightly more performant mode is to set things up in what they call cluster mode. And cluster mode actually divides the chip into 4 quadrants. And so every quadrant has an affinity with various types of this on-chip fast memory. Right? So in quadrant mode, the directory entries for these addresses are stored here. And the directory entries for these addresses are stored here. So the bad part of this is that because things are not randomly sorted around, memory has different performance characteristics depending on the address you ask for. The good thing about it is if you care, you can lay out your data in memory to get much better access times as well. Yeah, so that's Phi, and hopefully you can have some fun playing around with it. There's a pretty good slide deck on what's going on with it. Yeah, I'm going to stop a little bit early, but are there any questions? So my summary is, what would you say is the biggest, what is the big idea from this lecture? If last lecture introduced coherence and told us about protocols for executing coherence, this lecture says what? It's about how to scale coherence, right? And what's the big idea behind scaling coherence? Stop shouting, because most of the time, you only need to talk to a small number of processors in the system, so let's work it out with point-to-point messages, and that's how we're going to scale. Okay? So I'll stop there, a little bit early today.